everyone, let's just jump right into it. Welcome to today's explainer. We're going to embark on a pretty incredible journey today. We're looking at the messy, dynamic, constantly changing physical world around us. And we're going to learn how to translate those physical changes into the elegant, universal, mathematical language of chemistry. If you've ever found yourself wondering what's actually happening at that invisible atomic level when things transform right in front of your eyes, well, you are in the exact right place.
Here's our roadmap for this explainer. 1. The world of chemical reactions. 2. Spotting a chemical reaction. 3. The language of chemistry. And 4. Balancing the equation.
Let's kick things off with part 1, the world of chemical reactions.
The source material gives us this wonderfully straightforward definition. It says whenever a chemical change occurs, we can say that a chemical reaction has taken place. But what does that actually mean deep down? It means atoms are busy. A chemical reaction literally involves the breaking and making of bonds between atoms to produce completely new substances. The atoms themselves don't just magically disappear, and new atoms don't just pop into existence out of thin air. They're just rearranging their connections. It's like a giant puzzle being taken apart and put back together in a totally new way.
Moving right along to part 2, spotting a chemical reaction.
So how do we actually know that these invisible atomic bonds are breaking and reforming? I mean, we don't have microscopic vision, but we don't need a powerful microscope to know a reaction happened. We just need to know what physical clues to look for. Take this classic lab setup. If you drop solid zinc granules into a flask and then carefully pour in some dilute sulfuric acid, things get really interesting really quickly. You'll see this super active bubbling around the zinc. That right there, that is highly flammable hydrogen gas being rapidly formed. And if you were to actually touch the outside of that glass flask, it would feel noticeably hot to the touch. The atoms are violently rearranging themselves inside.
From classic experiments just like that zinc and acid one, we can confidently point to 4 undeniable signs that a chemical reaction has taken place. If you see a change in state, a change in color, the evolution of a gas, or a change in temperature, you, my friend, are witnessing chemistry in action. Which brings us to part 3, the language of chemistry.
Okay, so now that we know how to spot these reactions out in the wild, we run into a bit of a communication problem. How do we efficiently describe what's happening on paper? I mean, sure, we could write out a big clunky sentence like, when a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. But scientists, they love a good universal shorthand. So the first step is creating a word equation. We just write magnesium plus oxygen, and then we draw an arrow pointing to magnesium oxide. The substances that are actually undergoing the change, in this case magnesium and oxygen, those are called the reactants. They always live over on the left-hand side. The brand new substance that gets formed, the magnesium oxide, that's our product, and it sits on the right. And that arrow, it's just acting like a one-way street sign showing the direction of the reaction.
But you know what? We can be even more concise than that. Instead of writing out the full words, we can just use chemical formulas. So magnesium becomes Mg, oxygen becomes O2. Magnesium oxide becomes MgO. And boom, we get Mg plus O2, arrow, MgO. This is what chemists call a skeletal chemical equation. It's great because it tells us the who and the what of the reaction, but there's a slight problem here. If you look closely and count the atoms, we've got 2 oxygen atoms on the left, but only 1 on the right. Since the mass isn't the same on both sides, this equation is technically incomplete. It totally ignores the law of conservation of mass. And remember, that law is an absolute rule of the universe. Mass can neither be created nor destroyed in a chemical reaction. And that leads us right into part 4, balancing the equation.
Take a look at this chemical equation. It shows iron reacting with water to produce iron oxide and hydrogen gas. As written, this is a skeletal equation. It contains a critical error. It violates the law of conservation of mass. In a chemical reaction, atoms cannot be created or destroyed. The total mass of the reactants must equal the total mass of the products. Get your pen and paper ready. I am going to demonstrate the 7-step hidden trial method to balance this specific equation in under 5 minutes. Balancing equations is a necessary skill for predicting the outcome of any real-world reaction. It ensures your chemistry remains grounded in the laws of physics. Step 1. Draw boxes around every formula. Rule: only add large coefficients outside the boxes. Never change the small subscripts inside. Step 2. Create a tally chart for reactants and products. Iron is 1 to 3, hydrogen 2 to 2, oxygen 1 to 4. This visual inventory prevents the small mathematical errors that often occur when tracking multi-atom molecules across a complex reaction. Step 3. Match iron oxide's 4 oxygen atoms by placing a 4 before the left side water molecule. Oxygen is balanced. Step 4. Unintended changes. This gave us 8 left side hydrogens. Resolve this by placing a 4 before the right side hydrogen gas. Balancing is an iterative process. Adjusting one element frequently requires a follow-up adjustment elsewhere, which is why a step-by-step approach is the most reliable way to find the solution. Step 5. Iron. Place a 3 before the left side iron to match the right. Step 6. Final scan. 3 iron, 8 hydrogen, 4 oxygen, all equal. Step 7. Remove the boxes and add state symbols, S for solid, G for gas. By verifying the math and adding the physical notation, the equation becomes an accurate blueprint of the reaction. This is our final, perfectly balanced equation. Remember the golden rule. To conserve mass, adjust only the coefficients. Never alter the subscripts. Now apply this framework yourself. Here is the skeletal equation for burning magnesium. Mg plus O2 yields MgO. Follow the 7 steps and share your balanced magnesium equation in the comments. This mathematical expression demonstrates a baseline rule of matter. When substances interact, they do not mix randomly. They are governed by a strict structural grammar. Every chemical reaction is a systematic reorganization. Atoms and bonds break apart and lock together with absolute geometric precision. We can map this abstract model directly to a physical reality. When solid carbon burns an oxygen gas to yield carbon dioxide, the matter behaves exactly like the geometric model. By analyzing these baseline equations, we can classify every elemental interaction based entirely on how mass and energy are exchanged. This matrix outlines the 4 distinct architectural typologies that dictate these interactions. Every interaction falls into one of these structures: combination, decomposition, displacement, or double displacement. To understand, the first typology is a combination reaction. This occurs when 2 or more distinct substances merge to form a single, entirely new product. Isolating the algebraic model, A plus B synthesizes into AB. This occurs during the vigorous hydration of quicklime. Calcium oxide reacts with water to produce calcium hydroxide, releasing massive heat. This equation documents precise phase shifts, showing solid and liquid merging into an aqueous solution. This structural assembly carries a distinct thermodynamic signature, inherently linked to the chemical synthesis. Forcing new chemical bonds to form frequently results in a massive release of systemic energy into the surrounding environment. We define this specific energy-releasing mechanic as an exothermic reaction. The burning of coal follows this exact exothermic rule. Carbon and oxygen combine, synthesizing carbon dioxide while expelling heat. Similarly, elemental hydrogen and oxygen gases combine to synthesize liquid water, again releasing energy as the new bonds lock into place. Combination is the primary mechanism of chemical synthesis, inextricably linked to this outward flow of thermal energy. The exact mechanical inversion of that structural rule is the decomposition reaction. In this typology, a single complex reactant is forced to yield 2 or more distinct products. Because established chemical bonds are highly stable, breaking them apart imposes an energy deficit. The reaction requires an intentional input of targeted external energy. We classify this energy-absorbing requirement as an endothermic reaction. 3 specific endothermic pathways are capable of severing these bonds. The first relies on thermal energy. When solid limestone is heated, the thermal energy forces the calcium carbonate to decompose into solid quicklime and carbon dioxide gas. The second endothermic pathway utilizes photonic energy, driven entirely by light. When white silver chloride is exposed to direct sunlight, incoming photons sever the bonds, forcing the compound to decompose into silver metal and chlorine gas. This photonic breakdown leaves a macroscopic physical record. The stark white powder shifts to a dull metallic gray as the pure silver metal isolates. An identical photonic decomposition happens to silver bromide, providing the foundational chemical mechanism that makes classic black and white photography possible. The third endothermic pathway utilizes electrolytic energy. Passing a continuous direct electrical current through a liquid bath severs the bonds of water molecules, violently decomposing them into distinct hydrogen and oxygen gases. Decomposition is never spontaneous.
It is the targeted dismantling of matter, dictated entirely by calculated external energy inputs. Beyond simple assembly and disassembly, chemical grammar also dictates elemental competition. This introduces the single displacement reaction. Here, a more reactive element actively usurps a less reactive element currently bound within a compound. The algebraic model illustrates this competitive usurpation, showing element A forcefully displacing element B. We observe a classic test case for this rule by submerging a solid iron nail into an aqueous bath of copper sulfate. On the exact surface of the nail, a precise microscopic atomic exchange takes place. Because iron sits higher on the elemental reactivity hierarchy, it possesses the chemical strength to force the copper out of the solution entirely, taking its place alongside the sulfate. We can verify this displacement through two observable physical proofs. The surrounding solution fades from vivid blue to pale green, while the displaced solid copper coats the iron in a thick brownish layer. This hierarchical rule is strictly reproducible. Highly reactive metals like zinc and lead achieve the exact same displacement against copper compounds. Single displacement proves that molecular bonds are not permanent fixtures. They are continuously governed by an absolute hierarchy of chemical dominance. We can expand this competitive hierarchy into a scenario of mutual, simultaneous exchange between two reactants. In a double displacement reaction, the constituent ions of two compounds seamlessly trade partners to generate entirely new chemical pairs. A primary example is the interaction between an aqueous sodium sulfate solution and an aqueous barium chloride solution. Looking at the atomic composition, we isolate the exact subatomic swap. The sulfate and barium ions cross paths, exchanging initial positions. The immediate outcome of this precise ion swap is the creation of barium sulfate, marked heavily by a new solid-state symbol. This newly formed barium sulfate is insoluble. It cannot remain dissolved in the surrounding aqueous liquid. The sudden creation of this white, insoluble solid is known as a precipitation reaction. It is an instantaneous shift in the physical state of matter. Double displacement demonstrates how a microscopic ionic reorganization instantly overrides a material's physical properties, forcing dissolved particles to solidify and drop out of solution.
We look around and we see rust forming on an old bike or a campfire burning. But what's actually happening down at the elemental level? Like, how do elements trade oxygen? This isn't just random chaos, you know? Chemistry is actually a fascinating, highly structured story of exchange. Elements are constantly negotiating, swapping pieces of themselves to create entirely new substances. And the main currency in this elemental marketplace? It's oxygen.
Okay, let's dive right into this and look at the first side of this transaction. Section 1, Understanding Oxidation, Gaining and Losing.
Here's your foundational rule. Oxidation occurs when a substance gains oxygen or loses hydrogen during a chemical reaction. I really want you to focus on that first part right now, the gaining of oxygen. I mean, it's right there in the name, right? Oxidation. When an element takes on oxygen, its entire chemical identity fundamentally shifts. Let's walk through some real-world examples to see this physical transformation in action. First, imagine taking standard copper powder and heating it up in the air. Oxygen gets added to it, and the copper undergoes the stark visual change, turning its surface into a thick black coating. That black coating is copper-2 oxide. Next, consider a strip of magnesium ribbon. If you burn it in the air, it reacts violently with oxygen to form a bright white powder known as magnesium oxide. And then there's sodium. When sodium reacts and combines with oxygen, it forms sodium oxide. The key takeaway here? In every single one of these distinct reactions, the core element is acquiring oxygen. As we know, every transaction has two sides. That brings us to Section 2, the process of reduction, the exact opposite.
This opposing force is called reduction. By definition, reduction occurs when a substance loses oxygen or gains hydrogen during a reaction. Again, let's focus heavily on the oxygen aspect here. If oxidation is the taking of oxygen, while reduction is the losing or giving up of oxygen. The substance is literally being reduced of its oxygen content.
To really picture this, I want you to think of it almost like a story of microscopic chemical theft. Remember that black copper oxide we created a few moments ago? Well, if we take that heated black copper oxide and pass hydrogen gas over it, the hydrogen swoops in and completely removes the oxygen. It actually reverses the process.
The oxygen is gone, and what's left behind? Pure, brown, solid copper. This exact same kind of theft happens in industrial extraction too. When zinc oxide is heated with carbon, the carbon acts as the thief, removing the oxygen to leave behind pure zinc and creating carbon monoxide in the process. We see it again with lead oxide reacting with carbon. The oxygen gets completely stripped away from the lead, leaving pure lead behind and producing carbon dioxide.
The pattern here is just as rock solid as the last one, because these oxides, the copper oxide, the zinc oxide, and the lead oxide, have their oxygen forcibly stripped away. They are reduced. They lose their oxygen, so they undergo reduction.
Let's just pause for a second to contrast these two side by side. Oxidation is gaining oxygen. Reduction is losing oxygen. They are the perfect antithesis of one another. Think about it. You can't have a transaction where someone only buys, just like you can't have a transaction where someone only sells. Let's see how this builds into the absolute most fascinating part of our explainer. We've looked at them separately, but now we get to put the puzzle pieces together in Section 3. Putting it together, redox two sides of the same coin.
So, the absolutely crucial point is captured perfectly in this quote from our source material. In reality, oxidation and reduction do not happen in isolation. Think about the sheer logic of that for a second. If one substance loses oxygen, meaning it gets reduced, that oxygen doesn't just, vanish into the void. It has to go somewhere. Another substance in that exact same reaction must gain that oxygen, meaning it gets oxidized. You get this amazing aha moment when you realize they're a total package deal. Because these two processes always occur together, we have a specific name for them. We call them oxidation reduction reactions, or much more simply, redox reactions. In a single redox reaction, one reactant gets oxidized while the other gets reduced. They operate in total tandem, perfectly balancing the chemical books every single time.
And looking at the complete chemical equations brilliantly illustrates exactly what we've been talking about, bringing the whole picture into focus. Take copper oxide reacting with hydrogen. The copper oxide is reduced down to plain copper, while simultaneously the hydrogen is oxidized into water. One loses, the other gains. It's the same with zinc oxide reacting with carbon. The zinc oxide is reduced to zinc, and the carbon steals that oxygen, becoming oxidized into carbon monoxide. Now consider a slightly more complex example. Manganese dioxide reacting with hydrochloric acid. The manganese dioxide is reduced to manganese chloride, so it's losing its oxygen. Meanwhile, the hydrochloric acid is actually oxidized. How? Well, remember our definition. It loses its hydrogen to become chlorine gas. In every single instance, you have this perfect synchronized dance of reduction and oxidation happening in real time.
Take a newly manufactured steel gear. If it is left exposed to the air, it begins to rapidly consume itself. The chemical forces eating away at heavy industry are the same forces that cause a forgotten bag of potato chips to spoil. Everything humanity builds and harvests is under constant attack from the surrounding atmosphere, specifically from moisture, acids, and oxygen. Protecting our infrastructure and food supplies requires constant engineering. We spend billions of dollars every single year just to replace the materials that rot away. Whether it is the structural beams of a bridge or the pantry staples in a kitchen, our creations are locked in a relentless cycle of environmental decay. When metals break down, we call the process corrosion. This happens when surrounding substances, like moisture and ambient acids, slowly deteriorate the material. Rust is the most common example. When shiny iron articles are exposed to humid air, they react by developing a thick reddish-brown powder coating. The visual evidence changes depending on the metal involved. Silver items, like this ornate tray, tarnish over time by developing a black coating. When copper surfaces are exposed to the environment, like the panels on this roof, they react by developing a distinct green coating. And if aluminum is exposed to salty coastal air, it develops white, powdery pitting along its surface. This oxidation strips away the metal's internal strength. As the material chemically alters, it loses its physical integrity. That material weakness leaves our transportation networks vulnerable. It eats through car bodies and compromises the thick hulls of massive steel ships. It also threatens civic infrastructure. Over time, iron bridges and safety railings are rendered structurally unsound as the metal flakes away. Because corrosion removes load-bearing mass, society must spend vast amounts of money annually to replace damaged metal before it triggers a collapse. Those atmospheric forces also target organic matter, steadily degrading our food supply. When foods containing fats and oils oxidize, they spoil. This condition is called rancidity. At the microscopic level, oxygen in the air forcefully bonds with long-chain fat molecules, tearing apart their original composition. This new chemical arrangement changes how the food interacts with our senses, resulting in a ruined flavor profile and strong, foul odors. Leave roasted nuts, like walnuts or peanuts, sitting in an open container, and this oxidation is why they eventually taste bitter or soapy. Prolonged exposure to air and light is also why cooking oils acquire a stale, almost paint-like smell over time. It is the same reaction that causes a stick of butter to turn sour if left unsealed at room temperature for several days. Just as iron crumbles under moisture, our biological fuel degrades the moment it meets the air. Because the atmosphere never stops attacking, simply building or harvesting is not enough. We must engineer active barriers to shield our resources. To prevent packaged potato chips from going stale on the shelf, food manufacturers physically block oxygen from reaching the product. They achieve this by flushing the bags with nitrogen, an unreactive gas, creating a safe atmosphere inside the packaging. Manufacturers also mix antioxidants directly into the food, and we store our staples in sealed, airtight containers to cut off the oxygen supply. These microscopic defenses mirror our massive engineering efforts, like applying thick coatings over raw steel to seal out ambient moisture. A puffed bag of chips and a freshly painted bridge are both tactical barriers, essential defenses in the persistent struggle to keep our world from dissolving.